Hello everyone. Welcome to another episode of Deep Dive Knowledge Talk. What specific advancements in quantum hardware have contributed to the surge in quantum machine learning, QML, applications on real hardware, as mentioned in the study?
Advancements in quantum hardware, such as improvements in speed, qubit quantity, and quantum volume, have significantly contributed to the surge in quantum machine learning QML, applications on real hardware. Imagine you have a toolbox, and over the years, you have added faster tools, more tools, and larger tools. These advancements make it easier and more efficient for you to build complex things. Similarly, in quantum hardware, the improvements in speed, the number of qubits available, and the quantum volume, which defines how big a quantum circuit can be effectively implemented, have made it possible to run more complex quantum machine learning algorithms effectively.
How does the study address the limitations of implementing quantum machine learning, QML, on quantum hardware, specifically focusing on techniques like encoding, ansatz structure, error mitigation, and gradient methods?
The study addresses the limitations of implementing quantum machine learning, QML, on quantum hardware by looking at various techniques like encoding, ansatz structure, error mitigation, and gradient methods. Think of it like this. When we want to use a special machine called a quantum computer to teach it how to learn things, we need to make sure it understands the information correctly. So, the study explores different ways to translate regular information into a language that the quantum computer understands. It also looks at how to structure the learning process, reduce mistakes that can happen, and improve the way the quantum computer learns from its experiences. By focusing on these techniques, the study aims to make sure that when quantum computers are learning, they do it as effectively as possible, despite the challenges of quantum hardware.
How does the study propose to overcome the existing bottlenecks related to applying quantum machine learning, QML, on real quantum devices, and what potential solutions are suggested for the future in this regard?
The study suggests several potential solutions to overcome the existing bottlenecks related to applying quantum machine learning, QML, on real quantum devices in the future. One solution is to improve the techniques for encoding classical data into quantum features more efficiently. Imagine trying to fit different shapes into specific boxes. We need to find better ways to put the right shapes into the right boxes to make everything work smoothly. Another suggestion is to work on loading and storing prepared quantum states while preventing them from losing their properties due to decoherence. You can think of this as making sure a fragile glass sculpture stays intact even when there's a lot of movement around it. Additionally, developing more efficient quantum algorithms after preparing the quantum states is crucial. It's like coming up with better and faster ways to solve a puzzle once all the pieces are in place. Furthermore, based on the type of algorithm being used, different challenges arise. For example, variational algorithms often struggle with certain aspects. By addressing these challenges specific to each type of algorithm, we can pave the way for smoother quantum machine learning implementations on real quantum devices in the future.
How does the study examine the fundamental concepts in classical machine learning, quantum computing, and quantum machine learning, QML? And how does it discuss potential future research directions in this domain?
The study explores the fundamental concepts in classical machine learning, quantum computing, and quantum machine learning, QML, by looking at how data is encoded and processed in these different approaches. In classical machine learning, data is encoded in bits, zeros and ones, while in quantum computing and QML, data is embedded as a quantum state vector in the Hilbert space, which allows for more powerful residues of data due to the exponential dimensionality of the Hilbert space. Regarding future research directions, the study identifies the need to establish standardized benchmarks to effectively evaluate the superiority of QML algorithms. It also highlights the importance of addressing limitations related to hardware and algorithms, such as finite sampling noise, to realize the full benefits of quantum algorithms. Additionally, the study emphasizes the shift towards practical demonstrations in QML, as the field moves towards becoming more empirical rather than solely theoretical. are kinds of the article.
Could you elaborate on how the study discusses the shift towards practical demonstrations in quantum machine learning, QML, and the significance of this shift in transitioning the field from theoretical to empirical research?
The study discusses how quantum machine learning, QML, is moving towards practical demonstrations rather than just theoretical proofs. This shift is significant because it helps transition the field from being based solely on concepts and theories to becoming more empirical. In simpler terms, instead of just talking about ideas, researchers are now focusing on showing how these ideas actually work in real-life situations. This practical approach helps validate the concepts and theories in QML by demonstrating their effectiveness and feasibility in action.